I'd like to talk about highly extendable modular voltage equalizer integrating cell and module voltage equalizers for series connected electrolyte double-layer capacitors. In large-scale energy storage systems, cell and module voltage equalizers are needed. Today, I will propose a modular voltage equalizer integrating cell and module level equalizers. This equalizer can offer high extendability. Experimental equalization test demonstrated efficiency of proposed equalizer. Here is the outline of my presentation. First, I'll explain cell and module voltage equalizers, its characteristics, and conventional cell voltage equalizers. Second, I will present the proposed modular voltage equalizer and its extendability. Next, I'll explain operation modes, and finally show experimental results. As a background, energy storage cells as an electrolyte double-layer capacitor needs to be connected in series because single cell voltage is low. However, the cell voltages gradually become imbalanced. When energy storage system is charged or discharged in imbalanced condition, these cells may lead to overcharge or over-discharge. Overcharge and over-discharge may accelerate degradation of cells. Also, this imbalance may decrease the amount of usable energy. So, cell voltage equalizers are indispensable to preclude the voltage imbalance issues. In general, large-scale energy storage systems comprise numerous series-connected modules, and each module contains several cells. So systems require cell and module voltage equalizers, but increase the system complexity and cost. In addition, module level equalizers should be extendable because the system scale varies depending on applications. Here, I'll explain constant current characteristics. EDLCs has wider voltage variation ranges than traditional secondary batteries. If this equalizer exhibits constant voltage characteristics, excessive current may flow under severely imbalanced conditions. So equalizers should desirably exhibit constant current characteristics shown in this figure to protect circuit. This slide introduces two conventional cell voltage equalizers such as string-to-cell and adjacent cell-to-cell. String-to-cell equalizer such as series resonant voltage multiplier eliminates voltage imbalance with two switches, so systems tend to be simple and low cost. However, voltage stress of switches and resonant capacitor depend on the number of cells. When the number of cells is extended to n, equalizers must be redesigned with reselecting components and adjusting the transformer's turn ratio, resulting in poor extendability. Adjacent cell-to-cell equalizer, such as resonant switched capacitor converter, offer high extendability. The system can be scaled up by adding unit circuit without redesigning equalizer. However, component count increases in proportion to the number of cells, resulting in system complexity and high cost. Here, I'm going to review the requirements for voltage equalizer. There are mainly three requirements. The first, simplified system and low cost, even in large-scale energy storage system. Second, equalizers should desirably exhibit constant current characteristics. Third, module-level equalizers should be extendable due to variation of application. So today, I'd like to propose a novel equalizer to meet these requirements. Here is the proposed modular voltage equalizer. Proposed equalizer is derived from combination of series resonant voltage multiplier and resonant switched capacitor converter. Both converters operate as cell and module level voltage equalizers respectively. Two equalizers are integrated by sharing switches. achieving simplified system and low cost. Switches in the resonant switch capacitor converter are replaced with diodes, and this part behaves as an unidirectional converter. Extendability of this equalizer will be explained in this slide. When scaling up the system, the capacitors in the resonant switched capacitor converter are connected to the adjacent modules in parallel. Right-hand figure shows the extension to 3-module system. The number of cells and the equalizer design of each module are fixed, while the system can be extended by adding modules. Here, I'll describe the operation modes. The fundamental operating principles of the series resonant voltage multiplier and resonant switched capacitor converter are nearly identical. Both converters contain series resonant tank, so both can exhibit constant current characteristics in discontinuous conduction mode. Right-hand figure shows waveforms in discontinuous conduction mode. The switching frequency is set to around half the resonant frequencies to operate in this mode. I'll explain operation of the series resonant voltage multiplier when B1 is the least charged cell in a module. This figure shows the equivalent circuit of the converter. The converter supplies AC current to the transformer secondary side. Coupling capacitors connected to the secondary winding are responsible for passing only AC current components. So, all cells as well as diode rectifiers and coupling capacitors are separated and grounded. Since all cells are connected in parallel, current automatically and preferentially flow toward B1. I'll explain detailed operation. Left-hand figure shows operation waveforms, and right-hand figure shows current path. A single switching cycle can be divided into modes 1 to 6, and modes 1 to 3 and 4 to 6 are symmetrical. The sinusoidal resonant currents start flowing in mode 1. Although the switching state is unchanged, the polarity of current is reserved in mode 2. QH is turned off before resonant current reaches 0, and the operation mode shifts to mode 3. Equalization current toward B1 can be expressed as the following equation. This RR is the total resistance in the current path. Assuming RR is 0, IB can be approximated as follows. It does not include cell voltages, indicating IB is constant even under severely imbalanced condition. Then I'll explain operation of the resonant switched capacitor converter. This slide describes the case the voltage of module 1 is lower than voltage of module 2. This part of module 2 transfers power to module 1. Here I'll explain the detail. Left-hand figure is waveforms and right-hand figures show current paths. In mode 1, the voltage of module 2 is applied to the resonant tank, and the resonant current flows. When the polarity of the current is reserved, mode 2 starts. Then QH is turned off before resonant current becomes 0, and the operation mode shifts to mode 3. Like the series resonant voltage multiplier, equalization current toward module 1 can be approximated as this equation. IM does not include voltage of module 1, indicating IM is constant. The prototype of a module consisting of 6 EDLC cells is shown in here, and its component values are listed in this table. Resonant frequencies are derived from parameters of series resonant tank. Output characteristics of the series resonant voltage multiplier was measured using this experimental setup. Variable resistances were used to sweep output characteristics. The bottom left-hand figure shows measured waveforms. the good agreement with the theoretical ones. These are the measured output current and power conversion efficiency. Horizontal axis is voltage. Output current characteristics agreed where the theoretical ones in DCM region exhibited constant current characteristics. Then I'll show results about resonant switched capacitor converter. The R1 was used to measure characteristics. The key waveforms demonstrate the proper operation. Output current characteristics agreed were the theoretical ones in DCM operation region. The equalization test was performed for 3 6-cell modules from the voltage imbalanced condition. Both cell and module voltage changed almost linearly at the beginning of the test, thanks to constant current characteristics. The standard deviation declined as low as approximately 33 mV at the end of the experiment. I'd like to conclude by making the following points. In this presentation, I propose the modular voltage equalizer, integrating cell and module voltage equalizers. The proposed equalizer achieves the simplified system and low cost by sharing 2 switches. In addition, this equalizer offers high extendability and system can be flexibly scaled up without redesign. I showed some experimental results. First, cell and module voltage equalizers exhibit constant current characteristics, and the measured output currents were nearly constant. Second, cell and module voltage imbalance were eliminated in the experimental equalization test, demonstrating the equalization performance.